So before moving on to the topic of discussion today, I'd like to comment one thing. So here the problem was that the entry-wise convergence for infinite dimensional matrices is not a strong notion of convergence. So for example, entry-wise convergence may not preserve the, may not behave nicely with the product of matrices. Okay, so in other words, you may have BM converging B to B entry-wise, then A times BM may not converge to AB entry-wise. So therefore, this entry-wise convergence is not at all behaving nicely with the product of the matrices, and that's because the convergence notion is too weak. So therefore, we should, if we actually want to resolve this issue, we should come up with a stronger notion of convergence. And the correct notion of convergence in this case is, don't think of this Q in that case. If T is infinite set, T is an infinite set, then don't think of this infinite dimensional matrix Q as just a matrix. It's actually an operator. It's operating on a linear space. And then you talk about convergence under the suitable norm called operator norm. However, this is completely beyond the scope of this course. I just wanted to make this comment. Okay. And that's all I'm going to say about this issue. Okay, so now let's consider on the stuff that we actually want to do today, which is invariant measures and stationary distribution. Now, quickly recall that a probability distribution pi, and we'll always denote it as a column vector, is a stationary distribution if pi transpose equals pi transpose times p, where p is the transition matrix. In other words, this basically means that for all state j, pi j should be equal to the sum of pi k times pkj, as the sum is taken over k belonging to S. Now, for a stationary distribution pi, we shall use p pi to denote the probability distribution of the Markov chain when the initial distribution is pi. So, in other words, this means for every n and for every I naught up, for every positive integer n and for every I naught, I1 up to In in S, for every state like that, the joint distribution of x naught equals to I naught, x1 equals to I1, all the way up to xn equal to In, the joint probability of this under p pi is precisely this probability here. So p pi I 0 times pi 0 I naught times pi 1 I2 all the way up to pi I minus 1 In. And this, as you see, is just the joint probability when the initial distribution is pi. So by writing p pi, we are just reminding ourselves that the initial distribution is pi. That's all. Now, why is it called the stationary distribution? It's called the stationary distribution because if you start the Markov chain at pi, in other words, if the initial distribution is pi, then this process xn becomes a stationary process. So in other words, more precisely, the joint distribution of xn all the way up to xn plus k is same as the joint distribution of x naught all the way up to xk for every n bigger than or equal to 1. So that tells you that this is stationary. In particular, all the xn's are identically distributed if the Markov chain starts with initial distribution pi. Okay, then each xn is identically distributed. In fact, each xn is therefore following the distribution pi. So it's stationary in the following sense. It makes the underlying process a stationary process. Now, the questions that we are going to answer in this lecture and the next is, what are sufficient, at least, conditions under which, what are conditions under which stationary distribution will exist? And it's a very generic question, but can we give a nice enough conditions such that we can get hold of a stationary distribution? Secondly, when it exists, is it unique? Now, these are the two questions that we are going to be interested in initially. And then we'll tell, of course, more stories. And in particular, I'll tell you how important the stationary distribution is for the asymptotics of Markov chains. Okay, under conditions under the Markov chain, the distribution, the limiting distribution of the Markov chain would be its stationary distribution. So these kind of things, when will it happen? These kind of things we'll discuss later. But one thing that we'll notice is that we'll give two examples, is that stationary distribution may not be unique when the Markov chain is not irreducible. So we'll actually see two such examples. So in other words, stationary distribution, the uniqueness of the stationary distribution has very strong relation with the irreducibility of the Markov chain. We'll see this in the next class actually. And also, when the Markov chain is irreducible and one state is positive recurrent, then the stationary distribution will exist and actually it will be unique. In fact, we will actually show, not today, but next, actually I most probably I'll give it as an exercise. And next class, we'll see that positive recurrence is also a class property. So therefore, if the Markov chain is irreducible and one state is positive recurrent, then all states are actually positive recurrent. And in this case, there will be a stationary distribution and actually it will exist uniquely. Now, the notion of stationary distribution, its existence, uniqueness, etc. In order to answer questions on this issue, we'll actually need another notion. So that is called the invariant measure. We'll talk about it later, but let's first start with an example. So let's recall a simple random walk on say 0 to 1 all the way up to 5 with absorbing variance. So essentially, if you are at the interior, so you start at 3, doesn't matter where you start, but the point is if you're at the interior points like 1, 2, 3, 4, you move to one of the neighbors with probability half. If you're either at 0 or at 5, if you are one of the boundary values, then you just stay put. You don't go anywhere. You just come back to 0 with probability 1 if you're at 0. If you're at 5, you come back to 5 with probability 1. Now, this is clearly not an irreducible chain because 0 is an absorbing state, so singleton 0 is a class. On the other hand, singleton 5 is another class. And 1, 2, 3, 4 is another class. So there are 3 classes as opposed to 1 class. So therefore, this is definitely not an irreducible Markov chain. Now, however, well, we can find stationary distributions. For example, if you start at 0 with probability 1, say, then of course, we are never going to move from there. We are just going to stay there only. Okay? So therefore, delta 0 is definitely a stationary distribution of this Markov chain. Similarly, if you start on 5 with probability 1, that also is going to be a stationary distribution. So delta 5 is another stationary distribution. Not only that, if you just take any probability distribution that, just put some mass at 0 and some mass at 5, then we are never going to go out of that. Because if you start, at 0, you'll stay at 0. If you start at 5, you'll start at 5. So therefore, the distribution that puts mass alpha on 0 and 1 minus alpha on 5 and 0 everywhere else, where alpha is a number between 0 and 1, 0 and 1 inclusive. So if you take such a distribution, this probability distribution is clearly a stationary distribution. You check it. If you are not comfortable, just check it, but it's a trivial verification that this is indeed a stationary distribution. So of course, what this says is that therefore stationary distribution is not unique in this case. In fact, there are uncountably many stationary distributions, as we can see. And this non-uniqueness is essentially an artifact of the Markov chain not being irreducible, as we will see in the next class.